So you've been there, right? You spend days, maybe even weeks, setting up this massive, deep neural network, only for it to just not learn at all. It's one of the biggest frustrations in deep learning. We think deeper is better, but then the very thing that's supposed to make it smart is what breaks it. Well, today we're going to get to the bottom of exactly why that happens, and more importantly, how you can fix it. I mean, the whole promise of deep learning is pretty simple, right? More layers equals more power. You see, each layer builds on the last one. The first layer might just spot simple things, like lines and edges. The next layer takes those lines and says, hey, that looks like an eye or a nose. And you keep going deeper until a layer can recognize a whole face. So yeah, in theory, deeper should absolutely mean smarter.
Okay, but if that's true, then why does training a really deep network so often feel like you're just slamming your head against a brick wall? You watch the training metrics, and they either totally flatline, or even worse, they just explode into complete chaos. So what gives? Well, the answer is all about a tiny, incredibly important signal that gets lost along a very, very long road. All right, to get this, we've got to talk about how these networks actually learn. The whole process is called backpropagation. Basically, after the network makes a guess, it calculates how wrong it was. Then it sends a correction signal, and this is the important part, it's called the gradient, backwards through all the layers. This gradient is like a little note that tells each layer, hey, you need to tweak your settings this much to do better next time. But, as you're about to see, in a deep network, that journey backward is a dangerous one. Okay, let's actually watch this in action. So imagine we're at the very end of the network. It's just made its prediction. It calculates a pretty healthy correction signal, a gradient of, say, 0.9. That's a nice, strong, clear instruction on how to improve. But here's the problem. As that signal starts its journey backward, it has to pass through every single layer. And at each step, it gets multiplied by some small number. Now, after just 10 layers, look at that. Our strong 0.9 signal has just withered away to less than 0.06. It's fading, and fast. And by the time that signal makes it all the way back to the first few layers, whoa, it's basically zero. The best analogy I've ever heard for this is it's like making a photocopy of a photocopy of a photocopy. After a while, all you're left with is a blurry gray smudge. The original instructions are just gone. They've totally vanished. In that, right there, is the infamous vanishing gradient problem. The correction signals for those crucial early layers become so ridiculously small that their weights just don't update. And think about it. Those first layers are the ones learning the most basic, fundamental patterns. If they can't learn, nothing else matters. The whole network stalls. It's literally like trying to build a skyscraper on a foundation of quicksand. It's just not going to work. Okay, so that's one way things can go wrong, but what about the flip side? What happens if those numbers getting multiplied on the way back are just a little bit bigger than 1? Let's say we start with a gradient of just 1.5 at the end. Seems harmless enough, right? Well, that tiny difference makes a world of difference. After traveling back through just 10 layers, that 1.5 has absolutely ballooned to over 80. Instead of fading, the signal is getting louder and louder at every single step. And when it finally gets to the first layer, yikes, the number is huge. It's this massive, overwhelming value. You know what this is like? It's like microphone feedback at a concert. That little squeak gets picked up, amplified, and looped back through until you have a deafening, ear-splitting screech. The signal hasn't vanished. It has exploded. And this is its evil twin, the exploding gradient problem. The updates to the weights become so insanely large and erratic that the whole training process just goes haywire. Instead of taking these nice, careful steps toward the right answer, the model is just chaotically jumping around, completely out of control. It's never going to find a good solution that way. So we've got these two nightmare scenarios. The gradient either vanishes into nothing or it explodes into chaos. So what's the deal? What's causing this? Well, if we're going to play detective, there are a couple of usual suspects we need to look at: the activation functions we choose and how we set up the network's weights in the first place. Okay, a huge part of the vanishing gradient problem comes down to the activation functions we used to use. Old school functions like sigmoid and tan, they've got this S shape. Now look at the flat parts at the top and bottom. The derivative there, that's the number that gets multiplied during backpropagation, is basically 0. So if you stack a bunch of these layers, you're just multiplying near zero by near zero over and over, and poof, your gradient is gone. But then along came a hero, ReLU, the rectified linear unit. It's so much simpler. For any positive number, its derivative is just 1, a constant 1. This is a game changer because it means the gradient can flow backwards through the network without getting squashed. It's like a perfect signal booster in every layer. So switching to ReLU is a massive first step. Huge, but it's not the entire solution. To really get a handle on these unstable gradients, we also have to be a lot smarter about how we kick off the training process to begin with. You might not think about it, but how you set the very first random weights for your network, it matters a lot. If you start with the wrong values, your gradients can vanish or explode before you've even processed a single batch of data. That's where smart initialization methods come in, like Gloro, sometimes called Xavier, and He initialization. Their whole job is to set those starting weights just right. Not too big, not too small. They do some clever math to make sure the signal can flow smoothly right from the get-go. And just so you know, He initialization is pretty much the go-to standard whenever you're using ReLU. Okay, so a smart start is crucial. But even with a good start, things can get a little wobbly during training. The internal state of the network can shift and drift, and suddenly you're right back in gradient chaos territory. So we need another tool in our toolkit, something that can keep things stable throughout the entire training process.
And that brings us to a really powerful technique called batch normalization. Honestly, the easiest way to think about it is like a little regulator that you stick between your network layers. Here's what it does. For every little mini batch of data, it takes the output from the layer before it and normalizes it. Basically, it rescales everything so it has a nice predictable average and spread. Then, and this is the clever part, it has 2 parameters that the network actually learns to scale and shift that normalized data. This lets the network figure out the best possible distribution for itself. By constantly recentering the data as it flows through, batch norm keeps the gradient signals stable and strong. It's a huge win. It makes training way faster and often gives you better results. All right, let's wrap this up into a quick, practical checklist for you. If you're staring at a training graph that's gone wild, here's what you do. First, your activation function. Ditch the old stuff and switch to ReLU. Second, your starting point. Make sure you're using a smart weight initialization, like He. Third, keep things stable during training by adding batch normalization layers. And hey, if you're still dealing with exploding gradients, there's one more trick: gradient clipping. It's a simple brute force method that just says, nope, the gradient can't go any higher than this value, putting a hard cap on it. You know, all these tools together have completely changed the game. They've let us build and train networks that are way deeper and way more powerful than we ever thought possible. For the most part, we've kind of tamed the unstable gradient. But it makes you wonder, right? As we keep pushing the limits, building networks with hundreds, maybe even thousands of layers, what's the next impossible problem we're going to run into? What's the next great challenge that's waiting for us just over the horizon?